Metal webinar series this year. We've had two great talks so far. First from Peter Beckett back in March, and then Richard Fuster last month. And today we have another exciting talk from Carmen Sánchez-García. Carmen is a postdoctoral researcher at the University, or Swansea University in Wales, and works on the effects of fire on soils and water quality. And amongst other published works, which I'm sure we'll hear more about in the seminar today, Carmen's work has looked at kind of ash and ash properties from sites across the world, which led to kind of a major review work which came out in Environment International last year, pulling together a global set of ash. I'm sure we'll hear a little bit about that later on. So today's talk is going to integrate many of these ideas, kind of echo some of the themes from the Peat Metal webinar series, and talking about ash properties and ash transport. We'll have about 40 minutes for the presentation itself, with plenty of time at the end for questions and answers. But if you've got any questions during the course of the seminar, feel free to pop them into the chat and we'll pick them up in the Q&A session. At the end of today's session, we'll have a reminder about the next month's webinar as well. So we'll keep an eye on that after today's session. So without further ado, I'll hand over to Carmen. Over to you.
Hang on, just to let everyone know, we are recording this.
Oh, yes.
So if you don't want to be recorded, keep your camera off. We'll turn the recording off during the question and answer session though. Hope to see some people's faces then.
Yeah, thanks Emma for the reminder. Over to you, Carmen.
Okay, thank you. So I will share and hopefully this works. Yeah, can you see the right screen? Yep.
Yep, looks great.
Okay, well, let's start then. So yeah, thank you to everyone for being here today, and to the Peat Metal team for the opportunity to present our work as part of this webinar series. So yeah, today I'm going to talk about post-fire impact to water quality and why we should care about ash when we talk about water contamination impacts after the fire. And at the end of the webinar, I'm going to present an online tool that we have developed here in Swansea to assess and predict some of these impacts. And just to highlight that, the work I'm going to present today is also the result of, the work from my colleagues here in Swansea from many years, and also for international collaborators. So yeah, let's dive in. So for those of us that might not be so familiar with fire, just wanted to highlight that we have many different types of fires in the environment, and perhaps most of you would be interested today in peat fires, like here. Can you see my cursor? No, my arrow? Yeah.
Yeah.
Okay, thank you. So yeah, so most of you will be most interested in peat fires, like in this photo here. We can also find forest fires, and perhaps this is, the image of most of us have when we think about wildfires. We also have other fires like savanna fires, and these are very different to peat fires, to forest fires. Savanna fires are very quick passing. They burn mostly the grasses. They burn really frequently, and the soil is not affected, or almost not affected. And these are, examples of uncontrolled fires, of what we call wildland fires or wildfires. But we can also use fire as a tool in what we call controlled fires. So for example, here, this is an image of an agricultural burn. And these are burns that are typically done at the end of the harvest period. And the aim is to, burn some of these vegetation residues and help the soil regenerate. We can also use fire to actually reduce the risk of wildfires, of more intense wildfires, and this is what we call the prescribed burns, which is the picture in the bottom right. And like I say, these fires are done to reduce the amount of vegetation in the landscape, or what we call in fire terms the fuel loads, and therefore reduce the risk of a more extreme fire in the case of that this happens. So all these different fires will lead to different effects on the environment. So today I just want to clarify that I will talk about uncontrolled fires, I will talk about wildland fires, and I will not talk about controlled burns. And when we talk about water contamination effects after fire, we have to talk about on-site effects and also off-site effects. So also one of the, probably more important on-site effects of wildfires is on soil and on soil erosion. So wildfires can enhance soil erosion by reducing the infiltration in the soil, by resulting in the loss of the vegetative cover, the vegetation, and also by altering the stability of the soil. And this is in many cases caused because of the heat flux that it can be produced from, from the fire, from the burning of that biomass into the soil. And, this will usually depend on the degree of burn severity, so how hot this fire burns. And, this post-fire erosion can also result in off-site effects. It can enhance flooding, it can enhance mud and debris flow. And therefore, if all this material is transported into rivers, reservoirs, it can result in water contamination. It can compromise water quality. So this is just an example from the US, just to illustrate some of these effects. This is quite an extreme example for UK context, but it's not that extreme for, for the US context. So this is the McKinney fire in California. The fire occurred in 2022, and quite a large fire. It was extinguished by an 80-millimeter storm that also resulted in a large debris flow. And this debris flow impacted the fisheries downstream in the Calumet River. So you can see this is just the news from around that time, that it caused a large fish kill in the Calumet River. Now, a year on the fire, a year after the fire, there had been very little recovery. And actually this image here in the middle is from a year after the fire. So you can see how the vegetation had pretty much not recovered. And all this soil was ready to be transported again, ready to go. So a year on, a 15-millimeter rain, much less intense rain, resulted in another debris flow. So you can see here in this picture, this is me. So I'm not short, I'm 170, and this is how high this debris flow came down at the delta of that channel. And this is the river here, so it was still looking, not like initially, but still looking quite turbid after this debris flow. So of course, the sediment that was transported would have an effect on the water, but there would be another key component, that is the ash, that it will play a key role in the water quality. But we don't have to go that far. So closer to us, this is the Saddleworth Moor fire around Manchester in 2018. And this fire also caused concern for the water quality surrounding the fire. But I believe Abby will talk about this fire in the next webinar series. This is another example closer where I am. In South Wales. So this is the Rigos fire from last year. So the fire started here. This is a north-facing slope. These north-facing slopes usually don't tend to burn here in the UK because, they are very humid. The moisture in the vegetation is usually high. But in this case, it did burn, and the fire moved towards the other hill slopes. So as you can see, these were very steep hill slopes. And there was a concern that the material that was deposited here after the fire would result in or affect the water quality of these two water bodies. One of them is a small lake, is a site of a special scientific interest, and the other one is a reservoir. So now, why do we care about wildfire ash? Why is wildfire ash important? So before we need to define what we consider as wildfire ash. So when we talk about wildfire ash, we define it as the particular residue that is deposited on the ground after a fire. And this is usually a mix of mineral materials and charred organic components. Now, I'm sure most of us in the audience at some point would have done a barbecue. So we can imagine that the ash is very light, it's very loose, and is therefore very easily transported by wind and also by water. the ash is enriched in nutrients, and this is because what the fire does is it concentrates in the ash the elements that are not volatilized. So it can be really rich in nutrients, which can have a positive effect, like we said before, for example, with the agricultural burns, and this is actually the basis of the slash and burn agricultural practices, because the ash, acts as a nutrient input to the soil, and it can have this fertilizing effect. Now, the ash can also be enriched in potentially toxic metals and metalloids. And when the ash is transported away from the burn area into water bodies, it can represent a potential pollution source. So if we, imagine a burned landscape, and this is again an extreme example, this is a forest that burned at high severity, so we can see the ground covered by ash. Now, if the topography allows for runoff and we have, enough rainfall to produce runoff, there is a risk that some of this ash might be transported downstream into rivers and reservoirs. And this is an example from Australia, where a large nutrient input resulted in an algae bloom in that reservoir. This is again a piece of news from around the same time, where it can also this ash that was washed into the river resulted in another fish kill. So these are, of course, environmental impacts. However, when these reservoirs, provide drinking water to cities and to towns, an event like this can compromise drinking water supplies in those areas. So we know that the ash is associated with a range of social, environmental, and economic impacts. And in order to assess and predict this impact, we needed a better understanding of ash chemical composition. And this is, where the study that Gareth was talking about at the beginning, this was the basis for developing this. So what we did to bridge this gap was to put together a comprehensive data set of ash chemical composition across the globe. And again, this is the work of many colleagues here and internationally. But, and we keep expanding this as we speak. So for example, in this image, you can see that South America at the moment is a gap, but we are receiving data. So we are very happy to keep expanding this data set. But at the moment, we have data from 29 sites. We cover 11 ecosystems and up to 150 samples in total. What we've done is we classify all these ash samples into high and low burn severity ones, just for simplicity. And some of these samples were collected before or after the rain. And I mentioned this because sometimes it's really difficult to get, well, ideally you would get ash before any rain, but sometimes it's very difficult to do this, simply because you cannot access the area, accessibility problems, or because it's not, you're not allowed to access the burn area until certain safety checks have been done. Sometimes, especially for large fires, they are often extinguished by a rainfall event. So sometimes it's virtually impossible to get the ash before any rain. So this is why some of our ashes, were collected before or after. And I will come back to this later on as to why this is important. So we brought all this ash to the lab and we analyzed for 25 chemical characteristics, including pH, electrical conductivity, and a range of nutrients, metals, and metalloids. And we looked at the total and the dissolved concentrations. And something that I would like to highlight about the data set, and one of the motivations behind it, is that although there had been some studies that had looked at ash chemical characteristics, especially only in the last decade, this is something that in the last decade has gained attention. But because we didn't have a standardized procedure, it was very difficult to compare this data. So this is something that we wanted to achieve with this data set, is that we can compare now all this data from different ecosystems and from different conditions. So we present today some of these main components that we found in the ash as an average, globally. And, I'm very happy to share with you the paper where we talk about this in detail, where the data is available. And yeah, but for now, the main components that we found was organic carbon, by large, and this is not surprising. This is because vegetation is often the main contributor to wildfire ash. And we also found carbon, aluminium, iron, and nitrogen as abundant elements. And especially the presence of aluminium and iron might indicate that some of these ashes have substantial soil component in them, because often it's not just the vegetation that burns, but it can also be the soil underneath. In other cases, it's simply very difficult to collect ash without also collecting some of the soil. So this might indicate some of these, the mineral soil presence. In terms of the metals and metalloids for human and ecosystem, of concern for human and ecosystem health, the more abundant ones that we found, and this is again average, it was manganese, zinc, lead, chromium, and copper. However, it is important to say that when we compare these concentrations with international contamination thresholds for soils and for sediments, all the average concentrations were usually below these contamination thresholds, except in a few cases, but I will go back to those later on. And just to say that we looked at nutrients, we looked at metals and metalloids, but other studies have looked at other potentially hazardous components in wildfire ash, and these might include polycyclic, aromatic hydrocarbons, cyanide, or corrosive compounds, amongst others. In terms of the pH and the dissolved elements, pH was high compared to the soil. 8.8 average, and this is because of high concentrations of alkali reactions in the ash. And in terms of the dissolved elements, we found the more abundant were dissolved calcium, sodium, and magnesium, and this might be because these are also the more soluble elements. Now, we looked also at the key factors that influence chemical characteristics in ash, and one of the main ones that we were expecting, and that we, it was the case when we checked the data, was burn severity. And perhaps it's worth describing what we understand about low and high severity. So we describe severity in the ash depending on the color. So ash from low severity fires would have a darker color, and this is because it has undergone a lower degree of combustion, so it's a more incomplete combustion. And then on the opposite side, you would have high ash from high severity fires is usually lighter, white, grayish, and this is because it has undergone a higher degree of combustion. It's a more complete combustions. So how did burn severity affect the chemical characteristics of the ash? So just very briefly, I will discuss some of the main trends that we observe. So for example, organic carbon and nitrogen were significantly lower in ash from high severity fires. And this is because the ash, at higher severities, there is a higher volatilization of organic compounds, and therefore they are lost during the combustion. Aluminium and iron, for example, we found the opposite trend, so they were significantly higher in ash from high severity fires, and it might be because of a similar case, because with high severity there might be a higher volatilization of the organic compounds that volatilize at lower temperatures, and therefore there might be an enrichment of other compounds like aluminium and iron with higher volatilization temperatures. And pH was also higher in ash from high severity fire because of a higher quantity of oxides and carbonates produced at high severities. So burn severity was a key influencing factor. Other factors that we found to be key determiners of ash chemical characteristics was the rainfall. So remember, we said some of the ashes were collected before or after some rainfall, and this we found to be a key influencing factor. I won't go into too much detail about it, but we can maybe discuss more of this in the Q&A if you are interested. And some other factors that might influence ash chemical characteristics, of course, the characteristics of the burn site. So the lithology, the soil type, the vegetation type, and if there is sequestered pollutants in the sites as well. So all this will have an effect on the characteristics of the ash. But Yeah, so it is important to say that the real impact of ash will depend on its dilution into the soil, into the sediment, and the water. So remember, when I was talking about averages, I said that some of these ashes showed higher concentration than the global average in metal and metalloids of concern. And this figure here just represents, is what we call a cluster analysis. So we basically had our global data set with all these ashes, all the chemical characteristics, and we run an algorithm to it to say, well, classify all these ashes into groups according to similar characteristics. And, we were expecting these two groups to happen, but it was surprising to see a third group. And when we looked into that group in more detail, it contained ash that have higher than average concentrations of metals and metalloids. And funnily enough, some of these ashes were from the UK upland sites, and some of these had some of the highest metal concentrations from all the analyzed samples globally. I will give you an example later on of one of the highest ones, which was from the area around Swansea. And the other sample was from a peatland in the Netherlands. Now, it's worth saying that the peats samples is the only peatland one that we have in the data set. So I would be very keen to expand on this to see if these trends, we find the same trend in other peatland samples, but I would expect so. And when we looked also in more details at some of these toxic metals and what particles they were associated with, we found that a lot of these toxic metals were associated with small size ash particles. And this is important because, these finer particles might be easier to disperse by wind and perhaps, easier to enter respiratory system. So there might be other effects associated with this. So therefore, with all of these, I just wanted to make the point that vegetation fires could mobilize sequester contaminants in the ash. So here, this is an example for lead, copper, nickel, and zinc. So in the first column, you would see the global average for all the, the average for all the samples together. In the same column, you can see the concentration for the peatland site in the Netherlands, and in the third column, the concentration for the pine forest in Swansea in South Wales. And you can see that the concentrations of lead, copper, nickel, and zinc are consistently higher than the global average. Now for Swansea, it is not a secret that around here we have a legacy of mining, so it is kind of expected. So here I have the map of the topsoil lead concentrations, and the circle highlights the area around here with high lead concentrations. And the same can be said for the area around the Peak District, the north of England. And in the case of the peatland, most people in the audience will be aware that peatlands are a well-known sink of pollution. And yeah, so as I say, I'm really keen to expand on this. And yeah, just to highlight that the risk of mobilization exists not only for metals, but for other pollutants as well, like asbestos, toxic organic compounds, or even radioactive materials. But this is an area that, we don't have a lot of evidence from. There is some evidence as well that fire might change chemical form of some of the contaminants, and this might affect potentially the bioavailability and the toxicity as well. Now, having said this, what can we do to assess and predict some of these impacts? So I wanted to introduce you this tool that the development of this tool was led by my colleague Hona Ineris here in Swansea in collaboration with the US Forest Service. It's called the Web Cloud Water tool. It's online, is open access, and it has been developed with the end user in mind. So here you have the link in case you can have a look. It predicts runoff and erosion, also ash transport and the loss of nutrients and metalloids, and therefore the water contamination risk. it accesses already the data that it needs. So it's been already preloaded. The only input that it needs from the user is a burn severity map to define the burn area and the burn severity. And if anyone is interested in using this and don't know how to create a burn severity map, get in touch and we can share the standard methodology. And also just to highlight that the tool can be used for actual fires, like for example, the Rigos fire that I was talking about before here in South Wales. So if there is a fire like that, when we have concern that there might be an effect on water bodies, we can use the tool to predict what this risk could be. But it can also be used for potential fires. So if anyone, if we want to know what could be the risk of a certain area burning to water quality, we can run simulations to estimate that risk. It works at the hill slope and also at the catchment scales. And one cool feature from this tool, and that water managers and land managers have found useful in the past, is that the tool can identify the hotspots of runoff, erosion, and contamination. And for example, here in this example catchment, in red and in orange, we can find the hill slopes that are at higher risk of erosion and ash transport. And why is this important? Because post-fire mitigation interventions, the resources that are usually available for this are limited in many cases. So this tool can help targeting these interventions. If there is interest in carrying them out. Some of these interventions, this is just some examples that are used around the world, but there is many. Some of these post-fire mitigation strategies can include mulching, can include seeding, physical barriers like from logs or heli mulching. And yeah, if you think this tool might be useful or that you might be able to use it, get in touch with us and we can support you. So the tool has been already applied in the US, in Australia. For the past year, I've been testing the tool in European catchments. So we can share some of the knowledge that we'd got from applying the tool to different sizes, to catchment sizes, conditions. And also, more importantly, if you think that, there is some capability that might help you to produce useful results that we don't have already in the tool, it might also be really good to hear some of that feedback. So yeah, and with this, I think I'm a bit early, but with this, I would like to finish and to thank you for your attention. And I would be happy to answer any questions.
Brilliant. Thank you very much, Carmen. I think we all
Thank you.
give Carmen a virtual round of applause there for that exciting and really interesting presentation. Brilliant. So has anybody got any questions that immediately spring to mind? I mean, I've been scribbling some comments down, but I'll see if the room have any questions either in the comments or pop your hand up.